Hello dear students, welcome back to Pen and Paper Chemistry. We continue with the topic of carboxylic acids, and this is video 4 where we are discussing the acidic character specific to carboxylic acids, not just carboxylic acids but organic compounds in general. What do you have to do? Yes, please keep your pen and notebook ready so that you have notes ready for offline reference. In the previous videos, I have already spoken to you about the acid and the conjugate base concept. So in today's videos, we shall be talking about the acidic character and comparing the acidic character of alcohols, phenols, carboxylic acids, etc. In the process, we will be revisiting the concepts that we've already discussed earlier. So the first one we talk about is the acidic character of alcohol. So we remember that alcohols do show acidic character to a small extent. So alcohols do react with very active metals like sodium, magnesium, etc. to liberate hydrogen. Yes, but they don't turn blue litmus to red. They don't react with bases to form salt and water. So what explains the slight acidic character of alcohols? Again, if we see the alcohol that we have written, so ROH, when it loses a proton, it is going to form RO negative. That means this is what we call as an alkoxide ion. Now, do you think that this alkoxide ion is stabilized by resonance? No, there is no stabilization by resonance, and at the same time you have alkyl group attached to the oxygen, which is again electron releasing. With the result, the acidic character of alcohols is much lower than that of carboxylic acids. Come to the acidic character of phenols. Yes, we've done this many a times earlier when we spoke about the properties of phenols. Yes, those videos are already there on the channel, wherein we've discussed the preparation and properties of phenol. So phenol, when it loses a proton, it forms the conjugate base, which is our phenooxide ion. Now this phenooxide ion is actually stabilized by resonance, wherein the electrons will move around in the ring, and we have a number of canonical structures formed. I want you to take the initiative and draw the canonical structures in the blank spaces provided. Go ahead, pause the video. First of all, take down these notes, and after you've taken down the first few points, please go ahead, draw the canonical structures of the phenooxide ion. And if you are not able to, I would suggest that you watch the video on resonance, or you may even like to go back to the videos on phenols. I want you to be confident. So I am not, no, these are not canonical structures. I want you to try them yourself. So we explain the acidic character of phenols on the basis of the resonance stabilization of the phenooxide ion, which is formed by the loss of a proton from the phenol. Now let us go on to the acidic character of carboxylic acids. Let us see what is formed when carboxylic acid loses a proton. So what is the conjugate base over here? Yes, it is the carboxylate ion. So coming from carboxyl, remember? Now carboxylate ion, can it undergo resonance? Yes, of course. Would you like to try and draw the canonical structures of the carboxylate ion? Go ahead, give it a try. So here the electron is shared between the carbon and the oxygen, whereas the pi electron moves towards the oxygen. So we have RCO 1, 2, 3, 4, 5, 6. and there are 2 electrons involved in the double bond. So, there is a negative charge over here, whereas this changes into a double bond, and I will have 1, 2, 3, 4, 5, 6, 7 and 8. With the result, we can represent the 2 canonical structures in the form of a resonance hybrid structure, indicating that the electron cloud is shuttling between the 2 oxygen atoms. Now, let us see and compare phenols and carboxylic acids. In the case of phenols, is there resonance? Yes, there is resonance. I hope you've drawn the canonical structures in the case of phenols. Yes, this is here. I have explained this thoroughly in the videos on phenols. These structures have been taken up in detail. Now, observe carefully where the negative charge is in the case of phenols. In the first structure, the negative charge is on the oxygen. The electrons are being held by oxygen, which is electronegative in nature. In structures number 2, 3 and 4, notice the concentration of the electrons. It is on the carbon atom of the ring. Which of the 2 is more electronegative, oxygen or carbon? Yes, oxygen is more electronegative, but our electron is presently focused on the carbon. Now, is that a stable structure? Is that a very good contribution towards resonance stabilization? No, because our carbon is not able to hold on to the electron as strongly as our oxygen can. On the contrary, look at the structures of the carboxylate ion formed by the loss of a proton. Negative charge, concentration of electrons on the oxygen, and oxygen is more electronegative compared to carbon. Take the second structure. Here also the oxygen is the electrons are concentrated on oxygen. So here the electron or the negative charge, the extra electrons are getting concentrated towards oxygen, which is stronger, which is able to hold on to the electrons. So when we do a comparison of the acidic strength of phenols and carboxylic acids, yes, they both are losing a proton and they are forming a conjugate base, but the conjugate base formed by the loss of a proton in phenol is not as well stabilized as in the case of carboxylate ion formed by the loss of a proton here. Why? Because in the case of phenols, the negative charge is on the less electronegative carbon in 3 of the canonical structures, whereas in the case of carboxylate ion, the negative charge is on the more electronegative oxygen. So, although our phenol does show acidic character, but the acidic character is not as strong and as good as shown by carboxylic acids. So, when I compare the 3 of them, aliphatic carboxylic acids, phenols and alcohols, the order of acidic strength would be aliphatic carboxylic acids greater than phenol, greater than alcohol. I hope this is clear till here, this point. Now, something interesting for you to do would be tabulate. What would you tabulate is make 3 columns: carboxylic acids, phenols and alcohols. And of course, we are still limiting ourselves to the aliphatic carboxylic acids. We are not talking about aromatic as of now. And under these 3 columns, discuss out of all the 4 properties of carboxylic acids about which we spoke about in the first video, that is a reaction with active metals, that is liberation of hydrogen. Oh sorry, not here, you will have to make another column here. So, reaction with active metals, you can make something like this. So, reaction with active metals, effect on blue litmus paper, reaction with sodium hydroxide, and reaction with carbonates and bicarbonates, and keep on ticking over here. So, whether this shows the property, yes shows the property, yes shows the property, yes shows the property. What about phenols? Do they react with active metals? Do they turn blue litmus? Do they react with bases? Do they react with carbonates and bicarbonates? Same way for alcohols, and this will be a good comparison as well as correlating what you are explaining regarding the acidic character of each one of them. Now, in our earlier compilation, we had also seen that aromatic carboxylic acids are more acidic than the aliphatic ones. You see, comparison of the pKa value. By the way, pKa is already covered. In case you missed that out, go back to the previous videos and we continue with the acidic character. Now, when we talk about the acidic character of aromatic or conjugated carboxylic acid, so I am taking the first one, aromatic, COOH. So, this is going to lose a proton and form a carboxylate ion. Because it is formed from benzoic acid, it will be called as benzoate ion. Now, when this benzoate undergoes resonance, what will happen? Again the same, electron will move on to the carbon oxygen bond. So, we will have the electron movement from one oxygen to the other. So, the electron pair moves here and the electron pair from the pi bond moves towards one of the second oxygen, and we have the resonance structure. Now, interestingly, if you see over here, there is the pi electron cloud over here, there is conjugation in the ring, there is alternate double and single bonds. With the result, the first structure that I drew over here can also take the form of this. Interesting, isn't it? So, I will again have 1, 2, 3, 4, 5, 6, 7 and 8 of the single bond, and same way the second structure that I have drawn can also be drawn as, yes, with a change in the position of the double bonds. In other words, there is of course a resonance in the carboxylate, in the COO group. There is also resonance happening within the ring due to the movement of the pi electron cloud. Now, we all know that the game of passing the parcel or tossing the ball around makes it more stable. The chances of the ball, the chances of the electrons remaining within this ring are very high, because here the electron is not remaining limited to any of the single carbon atoms. So, what happens when you compare the acidic character of aliphatic carboxylic acids, where you have two resonance structures, and you compare it to the acidic character of aromatic carboxylic acids, wherein yes, there is resonance within the COO negative group, but at the same time there is resonance in the benzene ring due to the pi electron cloud. So, which one do you think, which conjugate base do you think would be more stable? Yes, of course, the one formed by aromatic carboxylic acids. So, what can you say about the acidic character of aromatic carboxylic acids? Yes, they will be stronger as acids compared to the aliphatic ones. Also notice the carbon. The carbon here to which the C double bond O negative group, this group is attached, this carbon is having a double bond. That means it is an sp2 hybridized carbon. Whereas if I am talking about an aliphatic group over here, so instead of the R, let me put a CH2 and there is a CH3 along with this. Now, the carbon to which the COO negative group is attached over here is an sp3 hybridized carbon. sp3 hybridized means how much of S character is there? Only 1/4. That means the pull of the nucleus for these electrons will be lower. Whereas here the carbon is sp2 hybridized. So, what is the percentage of S character or the fraction of S character is 1/3. If I have to express it as a percentage, I will do 1/3 times 100. How is it 3? 1 of S and 2 of P makes a total of 3. Out of that 3, how many are S? Only one part. So, if you notice the percentage of S character is more, our S is spherical, it is closer to the nucleus because of its shape. On the other hand, P are dumbbell shape, because of which their distance from the nucleus is lower. So, if there is greater S character, there is greater pull for the electrons towards the carbon, making it difficult for it to lose its electrons. So, it is holding the electrons more strongly. So, the conjugate base, which is formed by the loss of a proton from the aromatic acid, is stabilized even further compared to, remember, we are talking about comparisons compared to the carboxylate ion formed from an aliphatic carboxylic acid. So, the same has been written over here in the notes. You may want to copy it down, as I always say, for future reference when you will not have the time to watch YouTube videos and you would be preparing for your exams. Have you noted all of this down? I will keep it on the screen so that you can note it. I might have to move the screen a bit to the right or the left. Okay, done. We observe the same effect of sp2 hybridized carbon in the case of the presence of a vinyl group, that is an unsaturated group present along with the carboxyl group. So, COOH or COO negative, howsoever you want to write. So, if you have an unsaturated carbon over here, there can be movement of the electron cloud. So, that means there are extra electrons available to move within the group. Moreover, our carbon here is sp2 hybridized now, with the result, of course, it is sharing its electrons with the bond, and at the same time it is able to hold on to, or the electrons are closer to the nucleus because of the sp2 hybridization. So, we say presence of vinyl group actually increases the acidity due to higher electronegativity of sp2 hybridized carbon. So, this is our resonance structure formed when the pi electron cloud undergoes conjugation with the CC single bond. Clear so far? Now, we did the generalization of the acidic character of aromatic carboxylic acids. What happens is the presence of substituents on the benzene ring definitely has a lot of effect on the acidity. We have seen in the previous video where we had compared the pKa values of nitrobenzoic acid and benzoic acid, and we noticed that nitrobenzoic acid is a stronger acid as compared to benzoic acid because of its electron withdrawing characteristics, and what was decreasing the acidic character was the electron donating groups. How is the electron donating group? Because here we have oxygen which is rich in electrons, and it will be happy to share its electrons with the benzene ring. Now when it does that, what happens? Yes, the benzene ring becomes rich in electrons. Will it allow the proton to go away easily? No, because our proton is actually positively charged. If this ring is rich in electrons, the proton will find it difficult to get away from the ring, and that is why we had written or jotted down the generalization: electron withdrawing groups increase acidic character, whereas electron donating groups decrease the acidic character. So, I have given you the generalizations here. Anything that takes the load off increases stability, making release of proton easier. So, we compare, yes, it's the same chart. And here we have the explanation. NO2 group is electron withdrawing, resonance stabilization due to minus I effect. Cl group, F, Br, all halogens are electron withdrawing, increases stability of the carboxylate ion. CH3 group on the other hand is electron donating, same way OH, because of the presence of lone pair of electrons on the oxygen. So, therefore, the acidic character actually goes down, and for a quick reference I have put a part of that chart over here. Now, a general observation is that orthoisomers, whether electron donating or electron withdrawing, are generally found to be more acidic than the others, meaning to say the orthoisomer, whether the presence is of the electron donating or the electron withdrawing, would be generally more acidic than the meta or the para. And when we talk about the meta and the para, electron withdrawing groups will actually increase acidic strength, whereas electron donating groups will actually decrease the acidic strength. So, what I have done over here is to give you a generalization. If there is the presence of electron withdrawing group, then it's the order of acidic strength would be para form, meta form, and then the parent compound, whereas in the presence of electron donating groups, it's the meta form, more acidic than the parent form, greater than the para form. Please remember that, and the simple minus R and the plus R effect, that is the resonance effect. Yes, we've already discussed it in the basics of organic chemistry. You might want to note down these points, and this is how we've listed the effect of the groups on the acidic strength. I will also try to post these notes onto the Google site Pen and Paper Chemistry. As I said, I will try my best to post it at the earliest. It's Pen and Paper Chemistry Google site. So, the channel and the site are the same name. All is free, all is for sharing, because we care. So, have you noted these points down? In the next video, I'll be taking up some reactions which are very, very specific to methanoic acid or formic acid. You know why? Look at this group, the naughty group which is present in methanoic acid. Of course, we have HC double bond OOH. So, we have the carboxylic acid group. But look at this group which is there, that is the aldehydic group, because of which our methanoic acid is actually able to show certain properties of the aldehydic group. You know which ones? Let's discuss it in the next video. Stay tuned, stay connected, and stay happy.